Welcome back to Applied Physics Lecture Series, Unit 4 Optical Fibers, Lecture 8 Acceptance Angle and Numerical Aperture. What is this acceptance angle? To understand the acceptance angle, first of all, recollect the principle behind the propagation of light in optical fibers. So that is total internal reflection. In order to notice such a total internal reflection, one condition is mandatory. That is theta I is greater than theta C. That means the angle of incidence must be greater than critical angle of incidence. To obtain this condition, three angles are very important. One is acceptance angle, second one is angle of refraction or refracting angle. Based on these two, we will achieve the condition for total internal reflection, which is theta I greater than theta C is possible or not. Simply, acceptance angle can be defined as the maximum angle of incidence at the core region of the optical fiber. As a result, the light ray may enter the optical fiber and it will undergo total internal reflection. If such a angle of incidence is capable of satisfying the condition of total internal reflection, simply that maximum angle of incidence will be called as acceptance angle. So that the exact way of defining acceptance angle is the maximum angle of incidence to the axis of optical fiber at which the light ray may enter the optical fiber so that it can be propagated through total internal reflection. So to get the expression for acceptance angle, some small geometry is required, and that geometry is represented here. So this cross section is representing core and cladding regions of the optical fiber. Here core region is the innermost region whose refractive index is represented with N1. And we are having the middle coaxial region named as cladding, and its refractive index N2 is represented in this geometry. And we are having air medium also, that is in front of the core region always air medium is there. The refractive index of air is represented with N0. And here alpha I is the angle of incidence and alpha R is the angle of refraction and theta C is representing critical angle of incidence. And here we can able to form a right angle triangle ABC, and here we are having two boundaries or interfaces. One is representing with A known as air core boundary or air core interface. And another boundary is B, which is nothing but core clad boundary or core clad interface. Basing all these into the consideration, now I am going to explain how to get the derivation for acceptance angle. See here, light is projected into the core region of the optical fiber from air medium with angle of incidence alpha I. So that is light is entered into the core region of refractive index N1 from air medium of refractive index N0. In the core region, it will suffers with refraction and it will produce as angle of refraction as alpha R, and it will incident on second interface or boundary which is represented with B known as core clad interface. At this interface, we will decide whether the light ray is undergoing total internal reflection or not based on the angle of refraction. So the light is launched from medium of refractive index N0 into the core of refractive index N1. There it enters to the fiber from air medium at an angle of incidence alpha I at the point A. Already I mentioned point A is nothing but boundary of air core interface or air core boundary. So the angle of refraction at A is alpha R. This ray undergoes total internal reflection at B. B is nothing but core clad interface at an angle theta. The minimum angle for total internal reflection is theta equals to theta C. That means the angle of refraction should be minimum 90 degrees. Here we form a triangle. So it is a right angle triangle ABC in which alpha R becomes 90 minus theta. Applying the Snell's law between air and core medium, that means at boundary A, we will get N0 sin alpha I equals to N1 sin alpha R. So from this sin alpha I equals to N1 sin alpha R by N0. So here alpha R is nothing but 90 minus theta. Then it can be written as N1 sin in place of alpha R 90 minus theta by N0. Then you will get N1 cos theta by N0. Say this is equation number 1. If theta is less than theta C, the ray will be lost by the refraction. That means it goes away by grazing along the cladding. Here the limiting condition is when theta equals to theta C, alpha equals to alpha I maximum. So we have to achieve at least this condition. Now this equation 1 can be written as sin alpha I maximum equals to N1 cos theta C by N0. But cos theta C can be written as 1 minus sin square theta c under square root, because it is a right angle triangle. Sin square theta plus cos square theta is equals to 1. Therefore, cos theta can be written as square root of 1 minus sin square theta. So in place of theta, here theta c is there. That's why cos theta c equals to square root of 1 minus sin square theta c. So substituting the value of sin theta c, which is nothing but n2 by n1. So that is the equation, that is cos theta c equals to square root of 1 minus n2 by n1 whole square. Then sin alpha maximum becomes square root of n1 square minus n2 square by n1. And maximum angle of incidence will be called as acceptance angle. That's why acceptance angle alpha I maximum is equals to sin inverse of square root of n1 square minus n2 square by n naught. This is equation 2. Based on all these, the maximum angle is called as acceptance angle or acceptance cone half angle. Light is launched at the fiber end. Within this acceptance cone alone will be accepted and propagated to the other end of the optical fiber by undergoing total internal reflection. In this diagram, you can able to see in front of the core region of the optical fiber in the air medium. So we will form an acceptance zone. So thus acceptance zone is in the form of cone. That's why this is also called as acceptance cone. Observe the single light ray which is entered here. So that light ray is producing certain angle of incidence, and that light ray, that angle of incidence is capable of producing angle of refraction little bit greater than 90 degrees. Then it will undergo total internal reflection. In this way, we will create maximum angle of incidence. We will identify the maximum angle of incidence in front of the core region of the optical fiber on both upper and bottom of the axis of the optical fiber. Then joining the upper angle of incidence and lower angle of incidence to the axis of the optical fiber in the form of a cone. So that will becomes acceptance zone or acceptance cone. Then once you identified set a acceptance region which is in the form of cone, then any light ray which is incident in that angle of incidence region, in the acceptance cone region, it is automatically capable of producing angle of refraction as greater than 90, thereby it will undergo total internal reflection. If any light ray which is not incident in this acceptance zone, that light ray is not capable of satisfying the condition of total internal reflection, which is nothing but theta I greater than theta C, then it is not allowed by the optical fiber to further transmission. So it will lose the core clad boundary. Therefore, the maximum angle of incidence at the axis of the optical fiber in front of the core region, so it is capable of producing angle of refraction as a minimum 90. Then such an angle of incidence is accepted by the optical fiber for further transmission. That's why such a maximum angle of incidence at the core region will be called as acceptance angle. Then we have to identify one more feature, which is nothing but numerical aperture, which is always associated with acceptance angle. What is meant by this numerical aperture? In general, if you want to describe, if you want to define what is this numerical aperture, aperture means so wide opening, which is like in the form of a slit. The opening dimensions, that aperture dimensions are represented with a numerical number, then it will become numerical aperture. Or in terms of optical fibers terminology, the light gathering ability of the optical fiber is expressed in terms of numerical aperture. Because the main function of the optical fiber is it has to transmit as much light as possible. But in order to transmit, first of all, we have to send the light into the core region of the optical fiber. We have to gather the light. So more amount of light is gathered by the optical fiber, more number of light rays are in a position to transmit through the optical fiber. That's why light gathering capacity of the optical fiber is expressed in terms of numerical aperture. The efficiency of the optical fiber is also expressed in terms of numerical aperture. If an optical fiber which is having more numerical aperture value, then it will be considered as a very efficient one or a quality one. That's why numerical aperture is also called as figure of merit of optical fiber. And in other words, there is a relationship between numerical aperture and acceptance angle, and that relation is expressed as sine of the maximum acceptance angle will be called as numerical aperture. That is, NA is equals to sine theta A. We know already the expression is NA equals to sine theta A means, so theta A expression is square root of n1 square minus n2 square by n naught. Therefore, by substituting that value, Na is equals to square root of n1 square minus n2 square divided by n0. Here n0 is refractive index of air whose value is 1. That's why numerical aperture Na is equals to square root of n1 square minus n2 square. Already we know n1 and n2 are the refractive indices of core and cladding mediums respectively. So the formula for numerical aperture is, one way of expressing the numerical aperture is Na is equals to square root of n1 square minus n2 square. And we will get another form of expression for numerical aperture. The same n1 square minus n2 square under square root can be written as square root of n1 minus n2 and n1 plus n2. Then here we have to define fractional relative refractive index difference, which is represented with the delta. That delta can be written as n1 minus n2 by n1. We have to define this one. What is meant by this fractional refractive index difference? Here we are having two refractive indices, n1 and n2, core and cladding refractive indices. And out of these two, the refractive index of core represented with n1 is more important because core is the light guiding region. That's why relative fractional refractive index difference is represented with a delta, and the expression for delta is n1 minus n2 by n1. So from this, n1 minus n2 can be written as delta into n1. So say this is equation number 4 and substitute this equation 4 in equation 3, which is nothing but Na is equals to square root of n1 minus n2 into n1 plus n2. In that, in place of n1 minus n2, write down delta n1. Therefore, the expression for Na becomes square root of delta n1 into n1 plus n2. But most of the fibers, even though n1 is greater than n2, but n2 is nearly equals to n1. That's why we can able to write n2 is nearly equals to n1. Therefore, the reduced equation becomes Na is equals to square root of delta n1, and in place of n2 also have to write n1. That's why n1 plus n1, it will becomes 2n1. Therefore, n1 into n1 square written out of the square root. That's why it will becomes n1 into square root of 2 delta. Therefore, the another way of expressing numerical aperture is Na is equals to n1 into square root of 2 delta. For altogether, we are having two forms of expressions for numerical aperture. One is Na is equals to square root of n1 square minus n2 square, and another form of expression is Na is equals to n1 into square root of 2 delta. Thanks for watching.